All right there, people. Let's see if we can knock out a video real quick. Not gonna lie to you, this will be the second attempt because the first one, sound quality wasn't so good. Also, I filmed it upside down. So we're gonna go ahead and start with some conic sections. So just a couple reminders with the conic section. So conic sections come from if I took a cone, right, like two cones that are stacked on top of each other. If I take them and I slice them, right, a couple different ways, I can get four different shapes. Okay, so the first shape that we said we come up with is a circle. And so the equation for a circle is x minus h squared plus y minus k squared equals the radius squared. Okay, so that's the center, that's the radius. And then the second one we learned about was in ellipse. Okay, and the equation for an ellipse was pretty similar to a circle, right? X minus h squared plus y minus k squared. But for this one, right, instead of being equal to the radius squared, it's equal to 1. Okay, and then underneath there is a squared and b squared, and we'll talk about what do those mean in a second. And then the third one we learned is the hyperbola. Okay, so the hyperbola is more or less like the opposite of the ellipse. Okay, so if a circle is the set of points that are equidistant from one point, the ellipse are the set of points that are equidistant to the sum from 2 points, the foci. The hyperbola is the set of points, or the locus of points, that have a constant difference between them, right? So like with the hyperbola, the equation looks pretty similar. A squared minus y minus k squared over b squared equals 1, right? And I could also have written this as like y minus k squared minus x minus h squared, and then it would open, right? Like whichever one we're subtracting from is going to tell us which way it opens. So when I have a hyperbola that's subtracted with like the y term being subtracted from the x term, that's going to open, right? That's going to open like side to side. Excuse me. And if I flip these, then it would open up or down. Check out the Khan Academy if you have questions. And then finally is the parabola. I think the parabola is really like the one that's the weirdest of the four of these. The parabola, right, like a couple ways that you could write it, you know, I think we've been writing as like x minus h equals a times y minus k squared or something like that. We'll talk about those, or the Khan Academy is pretty good, but just remember, the parabola is just a set of points that are equidistant from a focus in a line called the directrix, but Khan is pretty good on that. Okay, so a couple things that you need to know how to do is, right, like, can I take an equation for something? Okay, so like if I have something like this, x squared plus 16 y squared minus 10 times x plus 96y plus 153 equals 0. Okay, so whenever I'm doing these, I like to take them and rewrite them by like grouping my x's, grouping my y's, factoring, and then moving the constant terms, right? Like these just numbers are called the constant terms, to the other side. Okay, so x squared minus 10x plus 16y squared plus 96y equals negative 153. Then I'm going to take it out and complete the square. So if you're in my class, we took those algebra tiles for like x squared minus 10x, right? That would be something kind of like this. That's our x squared. And then we would take the 10 rectangles and we would do 5 this way. Then we would do 5 this way. Okay, and then like actually completing the square, right? And for all these conic sections, it's almost always just like grouping and then completing the square and then just sketching it based on like how the foci look. So completing the square for x squared minus 10x, that's going to take like 25 little ones pieces to complete this. Okay, so I can take this and I can rewrite it as x minus 5 squared. The reason it's x minus 5 squared is that's the distance. That's like x and then 5 minus 1s and x and 5 minus 1s this way. Okay, so when I do this, right, these 25 pieces that we needed to complete the square, I just invented these out of nowhere. Okay, so to balance this equation, I also have to add 25 to this side. Then I'm going to do the same thing here. Just to make it easier, I'm going to start by factoring a 16 out of 96 and 16y squared, which factors to y squared plus 6y. Okay, then I can take this and I can complete the square again. Right, if I separate these, it'd be like 3 on one side, 3 on the other, and 9 little pieces to fill it in. But there'd be like 16 of these. Okay, so it wouldn't just be like that's y squared plus 6y. Right, and then it takes 9 pieces. But because we factored a 16, right, there'd actually be like 16 of these. Okay, so I'm adding not 9 pieces, but I'm adding 16 times 9 pieces, which is 144. Okay, so I'm adding 144 up here. Then I can take this, and that's minus 153 plus 25 plus 144, which is 16. Okay, so this is starting to look like one of these conic sections. When I look at this, I can say to myself, okay, well, a hyperbola is like an x squared term and a y squared term being subtracted. It's not a hyperbola. It's not a parabola, right? In a parabola, either the x squared is term or the y squared is term, but not both. Not a circle, because like these coefficients would be the same, or the thing that it's being divided by would be the same. So this is going to be an ellipse. Right, with ellipses, usually we write them equal to 1. Okay, so I'm going to take this and I'm going to divide everything by 16 to make this equal to 1. Right, and that kind of shows us some certain information. So that's going to leave us x minus 5 squared over 16. Right, 16 divided by 16 is 1. So plus y plus 3 squared over 1, that equals 1. Okay, so we took this equation, completed the square, and we rewrote it as a standard form ellipse, just like this. Okay, now I can sketch it. So the center is going to be, right, like what I have to plug in here to make this 0, that's going to be 5, and this is going to be negative 3. Okay, so something kind of like that. And then this like tells us how much we're going to stretch it. Okay, so right, like the horizontal dimension is going to be stretched the square root of 16, which is 4. 1, 2, 3, 4. 1, 2, 3, 4. So something kind of like this. That's the major axis of this ellipse. Okay, and the foci are going to lie on this axis, and we'll look at it in a second. And then it's going to stretch 1 vertically. That's the minor axis. So you get something that's kind of like this. Okay, that's kind of a crappy sketch, but whatever. Okay, so to find the foci in an ellipse, it's just going to be a squared minus b squared equals c squared. And in a hyperbola, it's just the opposite. It's just you add these together. Okay, so a squared is the bigger term. So it's going to be 16 minus 1, which is 15. So the foci are going to be a distance of the square root of 15 from the center. And we said the center was 5, negative 3. Okay, so the two foci are going to be the square root of 15. The square root of 15 is like 3.8 or 3.9. Like, so somewhere over here, somewhere over there, roughly. But it's going to be 5 plus the square root of 15, negative 3. And the second one's going to be 5 minus the square root of 15, comma, -3. Usually people just write them as like 5 plus or minus the square root of 15 just to show that there's 2 of them. Hopefully that helps. Check out the conic section worksheet if you have questions. The next one I'm going to show you was a parametric equation. So I was just going to pull the one from the 10.2.2 slide deck we did, but it had to do with a baseball player throwing a baseball. Lots of these have to do with like motion, right? Either, well, I mean, they could be anything, but oftentimes they happen to be motion. And it's like something is falling, like with the seagull problem, or something's being projected. I'm gonna show you a projection problem, but with the seagull ones or stuff that's, it's a similar concept, okay? So this one says, the outfielder is throwing the ball at 120 feet per second, okay? So like he's launching the baseball from here. Here's his hand releasing the baseball, throwing at an angle of 40 degrees. Okay, and I always like to think of these as right triangles coming down that way, just like this, okay? And they're asking, write a set of parametric equations. How far does the ball travel? And then finally, can you write a rectangular equation? Okay, so let's start with the parametric equations. The parametric equations, basically we're measuring 2 different things. We're measuring like the horizontal distance and the vertical distance, and both of these with respect to time. Okay, so we're gonna have like x of t equaling something, that's our horizontal distance, and then y of t also equaling something, that's our vertical distance, okay? X of t, that's the easier one usually to find, right? Because we don't have to account for gravity. X of t is this right here. So I can think of this as like the cosine of this angle, right? I'm gonna call this x. Because we know what this is, we know what the hypotenuse is. So I can say x of t is equal to the adjacent, sorry, let's write like this. The cosine of 40 is equal to the adjacent over the hypotenuse. I hope that's not too small for you guys to see. Then I can multiply both sides by 120, and you get x of t equals 120 times the cosine of 40 times the amount of seconds. That's the distance it's traveling horizontally every second, okay? This is what the exact value is, but you can also estimate it. Just make sure your calculator, make sure you put it in degrees. But if I do 120 times the cosine of 40, that's like 91.93. Okay, so I'm gonna move yt down. So I could think of x of t 2 ways. I could think of it as, this is the exact value, 120 times the cosine of 40 times t. Or I could like estimate it to 91.93 t. I'm gonna use the estimation just to kind of shorten some stuff up. Then I'm gonna do the same thing for y of t. Hey, y of t is gonna be this distance here. It's gonna be the same process. It would, right, I could say the sine of 40 equals y, let's call this y over the hypotenuse, which is 120. So you get 120 times the sine of 40 times the amount of seconds. That's y of t, which I can also estimate to 77.13. Okay, so these are like roughly equivalent. That's the exact value, that's the estimation. If you did this in outer space, right? If I threw a baseball in outer space, that's how much it would like vertically be changing every second. Okay, but because we're on Earth, I have to factor in a couple things. The first I have to factor in is the gravity. Okay, and the constant for gravity in feet is -16 times the amount of seconds squared. Then I'm going to put this in, 77.13 t. I also forgot to mention this baseball player, right, when he throws it, he releases it from a height of 7 feet. So I was just saying this like shifting a function up 7 feet. Okay, so this quadratic equation we have is going to give us the vertical height of the baseball with respect to time. This one, x of t, is going to give us the horizontal distance with respect to time. Okay, so the first question was asking, write 2 parametric equations, we just did. The second one is saying, how far does the ball travel before it hits the ground? When I'm thinking about hitting the ground, I'm thinking about like using this, right? So basically, okay, so this is gonna pass through 0, 7 when he releases it. There's some negative, I know it's like really hard to see. There's like some negative part of the parabola here that I don't really care about, right? Because this is like seconds and this is the height. So I'm just looking for what's the y-intercept this way over here. Okay, and that's gonna tell me how many seconds it's taking, because this is like t and this is y of t. How many seconds does it take for that baseball to hit the ground? Okay, so if you have one that you can factor it. If you don't have one that you like, this one you can't factor, I don't think. So I'm gonna use the quadratic formula. Negative b plus or minus the square root of b squared minus 4 times a times c divided by 2a. Okay, and then a is gonna be negative 16. B is gonna be 77.13. C is gonna be 7. If I take this and solve it, negative 77.13 plus or minus the square root of 77.13 squared minus 4 times negative 16 times 7. While I'm doing this, right, if you have access to like a graphing calculator or Desmos, that's easier. But if you don't have one, you can always use this. If I do this, 77.13 squared, the square root. The square root of 77.13 squared minus 4 times negative 16 times 7 equals 79.98. Okay, so negative 77.13 plus or minus this value here, right? And this is going to be negative 32. So it's like negative 77.13 plus or minus 79.98 divided by negative 32. Okay. If I took this and added it, right, that's going to be like, let's just do it, negative 77.13 plus 79.98 divided by negative 32. I get this like, this is where my sketch is. That's this guy right here, which I said like, we don't really care about. Okay, I wanted to find this one, okay? So I'm going to do negative 77.13 minus 79.98 divided by negative 32. You get like 4.9 roughly. So that tells us this value right here, I'm going to say is roughly 4.9 seconds. So that's the second question, okay? How many seconds does it take for that ball to hit the ground? Roughly 4.9 seconds. The last question, or what they were asking though, was how far does it travel? If I know the time it takes to hit the ground, then I can take it and I can plug it into x of t. Okay, so if I do 91.93, 91.93 times 4.9, you get like 450.45 feet. So that's how many feet the ball will travel till it hits the ground. The last thing this was asking was, right, can I write a rectangular equation? So this is a parametric equation where I have like these two variables with respect to time. Rectangular equation, I'm going to take one of these and I'm going to solve it for time and then plug it in to effectively remove it by like subbing it out, which can be useful, but just know like we're losing information when I do this, okay? So I'm going to graph this. Or actually, let's just do it first. So x of t was equal to 91.93 t. If I take this and solve this for t, I get t equals x over 91.93. If I take this and I plug it in here, so now instead of y of t, this is like y of x, which is just y equals negative 16 times x over 91.93 squared plus 77.13 times x over 91.93 plus 7. So you get something kind of like this. If I took this equation, right, and graphed it in Desmos, or if I solved it with the quadratic formula, I would end up getting this, right, as the intercept. Because this one right, if I'm graphing this, for this one now, we're graphing like horizontal time, or horizontal distance, and vertical distance, okay? So you'd still get an upside down parabola, but it's gonna be much bigger. Because this is measuring, and this would still be 0.7. But over here, this intercept would be, 450.57, 0. Okay, so this one gets us a solution here, but just know that like we're losing something here, we're losing time. Sometimes with parametric equations, people put like t equals 1. They kind of put these points on there to kind of show you what that other variable is. T equals 4, and they might also put arrows on there to show you what's going on here. Hopefully that helps. I think for the test, I would just ask you to write this. I wouldn't ask you to solve. Like this one, we can solve pretty easy. This one's kind of a beast. So I might just ask you to like do something like this, especially with those little yellow calculators. Okay. Then the final thing was like solving parametric equations by turning them into rectangular graphing form and then making a sketch. Okay, so something like this. X of t equals -4 plus 3 times the cosine of t, and then y of t equals 9 minus 7 times the sine of t. Okay. If I took these and graphed these, like if you plug this into Desmos, this one, well, let's do this one first. This one would be like, right, some sort of sine curve, right? It'd be shifted. It'd be up 9 and stretched a certain way. And then this one would also be like this, okay? So you get like two like this. I'm gonna take this and I'm gonna rewrite it by solving for cosine or sine. If it's a different one like secant or tangent, I'm gonna do the same thing. I'm gonna solve it for the trig function. So this one, I could like start by adding 4 to both sides, right? Plus 4, and then divided by 3. That equals the cosine of t. And then for this one, I could do the same thing. Y minus 9 divided by -7 equals the sine of t. Okay, then I'm gonna use Pythagorean identity. And in this case, I'm gonna use cosine squared of t plus sine squared of t equals 1. Then I can take these and like think about doing that with these. Okay, so x plus 4 over 3 squared is x plus 4 squared over 9 plus y minus 9 squared over 49. 1 squared is just 1. So you get something like this. That's an ellipse. That's an ellipse. This ellipse is centered at 1, 2, -4, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's the center of our ellipse, and it's going to stretch 3 this way, 3 that way, and then it's going to stretch 7 up and down. Okay, so you get something like this. And then the foci would be 49 minus 9, which is 40. Take the square root of 40, which is 2 root 10. 2 root 10 is like 6.3 or 6.4. So the foci would be like something like that, Okay, hopefully that helps. Smash that like and subscribe video. Leave a pleasant comment in the comments below. If these are helpful, I can make them in the future, time permitting, but I appreciate you guys watching.